Hello and welcome back to the Fluid Mechanics course. In this lecture, we will learn about the concept viscosity of a fluid. Viscosity is a property that describes the fluidity of a liquid. To better understand this concept, 6 sub-concepts: stress, shear stress in a fluid, no-slip condition, velocity distribution, and gradient will be discussed in this video. The first sub-concept, stress, is discussed next. Stress, denoted by the symbol sigma, is force per unit area. For example, consider a solid cylinder resting on a flat, rigid surface, is acted upon by a normal force F. Assume that the cylinder is in static equilibrium. This means that a reactive force R, equal and opposite to F, is developed. These equal and opposite compressive forces generate stress inside the solid cylinder. The magnitude of this stress, at a given cross-sectional area, is given by sigma equals F divided by the cross-sectional area A at that location. Note that stress, normal or shear, developed inside the material is responsible for its failure. Consider another solid body as shown in the figure, acted by 2 equal and opposite forces. Calculate the average stress generated at 2 cross-sections, 1, and 2, of this solid body. The average stress at 1 can be calculated as 79.6 Newton per meter square. At 2, the stress can be calculated as 7,961 Newton per meter square. This example shows that the average stress is very high at the neck region of the solid. Now, we will review the concept shear stress. Shear stress, tau, is shear force per unit area. Consider a rigid solid cylinder fixed at one end, as shown in the figure. In this example, a force F acts tangential to a given surface with area A. At static equilibrium, this shear force will be balanced by a reactive force R. These two forces can generate shear stress inside the body. The shear stress tau, produced on the surface, will be equal to the shear force divided by that area. Now, to understand how shear stress develops in a fluid, consider this example. A fluid is filled between 2 large parallel plates, where one plate is fixed and the other is pulled with constant force F, and it is moving with a constant velocity v. Since the plate is moving with a constant velocity, the external force must be balanced with an equal and opposite force from the fluid on the plate surface. Let tau be the shear stress developed on the solid-fluid interface. If the surface area of the plate is A, then the force F must be equal to tau times area A. Now we look at the next sub-concept, no-slip. To understand the concept no-slip condition, consider the example discussed earlier. The upper plate is pulled with a force F, and it is moving with a constant velocity v. The bottom plate is assumed stationary. The moving plate will pull fluid close to it with the same velocity, while the stationary plate keeps fluid close to it, as stationary. Mathematically, this can be written as, at y equals 0, fluid velocity is 0, and at y equals capital Y, fluid velocity is capital V. This means that fluid particle, in contact with the solid surfaces, are not slipping, but assume the same velocity of the surface. This is called as a no-slip condition. To understand the concept of velocity distribution in a fluid, consider the same example discussed earlier. We have seen that a non-slip condition implies that at y equals 0, velocity equals 0, and y equals capital Y, velocity equals v. Now, the velocity of fluid layers between the plates could be treated as a function of y. A possible linear distribution of velocity of fluid layers is shown in figure. This variation of fluid velocity with distance y, from the stationary plate can be considered as a velocity distribution. This can be represented as a mathematical equation as well. And finally, a mathematical subconcept, gradient, is discussed next. The gradient of a function, at a given point, is its derivative at that point. This is the slope of the line tangential to that point, in that functional curve. Consider a function y equals fx as shown in the figure. The derivative, dy by dx, is the slope of the curve at a given point. If we know the velocity distribution as a function of distance y, as mentioned in the previous example, we can calculate gradient of velocity at a given location. Now you have a better understanding on necessary prerequisite concepts required to learn the concept viscosity of a fluid. Please go to the video lecture 5 that describes the concept viscosity. Thank you for listening.